Hello and welcome. Here's a question. Do Roman paramedics refer to IVs as fours? In this section, we're going to look at taking derivatives and integrals and arc lengths and surface areas with parametric curves. Let's go to notes. Starting with derivatives, if we have a curve in parametric form, we can still calculate the slope of the tangent curve. What we can do is we can start with a chain rule where we're going to write this version of the chain rule, dy dt equals dy dx times dx dt. So it's kind of like y is a function of x and x is a function of t. So if we want to take the derivative of y with respect to t, we can first take the derivative of y with respect to x and then multiply it by the derivative of x with respect to t. So if we want to figure out, if our goal is to find out what dy dx is in this case, we can just solve for dy dx in that chain rule equation by dividing the dx dt over to the left. So switching the sides, we would end up getting dy dx, which is the slope of the tangent line in the xy plane for this parametric curve, equals dy dt over dx dt. Now to get the second derivative, we can compute the second derivative of y with respect to x is just the derivative with respect to x of the first derivative. Now to take the derivative with respect to x of the first derivative, we can again apply this same kind of rule. So instead of y here, now we just have y prime. So we have dy prime dt over dx dt. So we can write that the second derivative of y with respect to x is dy prime dt over dx dt, where y prime means dy dx. Sometimes when you have just that prime notation, you lose whether or not it's derivative with respect to x, or in this case, maybe with respect to t. Here, the y prime represents dy dx. So that's where you fill in the first derivative in order to get the second derivative. Looking at example 1, it says find the tangent to the curve x equals t squared and y equals t cubed minus 3t when t equals root 3. It shows a picture of that curve over there in figure 1. So our first goal is going to be to find dy dx. That'll give us the slope of the tangent line at any value of t. Oops. Right. Find dy dx. Well, to find dy dx, we need to get dx dt and dy dt, and then we can divide those two. So dx dt here will be the derivative of x with respect to t, which is 2t. dy dt is the derivative of y with respect to t. That should be 3t squared minus 3. So then dy dx is dy dt over dx dt, which is 3t squared minus 3 over 2t. Now we can leave our dy dx like that, but in a future example, example number 2, we're going to need to have a simplified form of that. So let me just take a couple of steps to simplify. We can factor out the 3 from the top and we get 3 times quantity t squared minus 1 over 2t. Then we have a 3 over 2 that can be pulled out as a constant in front. And then we can divide the t into the t squared and the 1. So we'll get 3 over 2 times the quantity, let's see, t squared divided by t is t, and then minus 1 over t. So 3 over 2 times quantity t minus 1 over t. Now we can figure out what the slope of the tangent line is at t equals root 3. Find slope at t equals root 3. Slope of the curve and slope of the tangent line, they're referring to the same thing. The way we can write that is dy dx evaluated at t equals root 3 Here we'll get 3/2 times root 3 minus 1 over root 3. And if you work on that a little bit, you can eventually get that down to just root 3. Get a common denominator, try to combine the tops and see what you get. So then the last step is going to be to, second to last step, will be to find the point at t equals root 3. After all, to get the equation for the tangent line, we need to get the slope of the tangent line, which we just found, and the point that the tangent line goes through. So to figure that out, we're going to plug in the t value that we're at, which is root 3, into the original parametric equations. That'll give us an x-coordinate and a y-coordinate that the tangent line is going to go through. So plug in t equals root 3. Into x equals t squared, and you get x equals 3. Then plug in t equals root 3 into the y equals t cubed minus 3t. Plug that in there. And you end up getting 3 root 3 minus 3 root 3, which is 0. So the point is 3, 0. Lastly, we'll get the equation for the tangent line. Using point slope form, y minus y1 equals m times x minus x1. So that becomes y minus 0 equals root 3 times quantity x minus 3. And I can distribute the root 3 and write it as y equals root 3x minus 3 root 3 if you want. Or you can just leave it using that point slope form. That's fine too. So there's the equation for the tangent line at t equals root 3. Now actually, if you look at figure 1, you'll notice that there are 2 tangent lines at that point 3, 0, because the curve goes through 3, 0 twice. So the one that we found was the one that has a slope of positive root 3. So it was the tangent line for the part of the curve that's moving through the 3, 0 and increasing as it goes through 3, 0. If you looked at, it turns out t equals negative root 3, you'd still be at that point 3, 0, but then you'd have a negatively sloped tangent line. You'd have this tangent line that goes down as you go to the right. So for parametric curves, you could have more than one slope of the tangent line, or more than one tangent line at a particular point if the graph of the parametric curve ends up crossing itself. So that's what this little note is saying down here. Note that there are 2 tangent lines at the point 3, 0, one at t, root 3, and one at t, negative root 3. At t equals root 3, and one at t equals negative root 3. I don't know what I'm saying here. Example 2 says find the second derivative of those same parametric equations. So the second derivative of y with respect to x is going to be the derivative with respect to t of the first derivative, so it's dt of dy dx, over the derivative of x with respect to t. So to get the second derivative, you take the derivative of the first derivative, and this is just how you take the derivative using parametric equations. You do d of your function dt over dx dt. Well, we have dy dt. In fact, we have a nice simplified version of sorry, we have dy dx. We have a nice simplified version of dy dx. It's 3/2 times quantity t minus 1 over t. That we got from example 1. We're going to copy that down. 3/2 times quantity t minus 1 over t over, and then dx dt we also found in example 1. Dx dt was 2t. Now let's finish taking the derivative on the top. We have 3/2 times derivative of t, which is 1. Derivative of 1 over t is negative 1 over t squared. That minus negative turns into positive. And then the only last thing maybe to do is clear out that little fraction, which I'll do by multiplying the top and the bottom by t squared. It's just nice not to have fractions inside of fractions. And in fact, we can move this this 2 down to the bottom here. So we'll have 3 times t squared plus 1 over 4t cubed. So there's the second derivative of y with respect to x, written as a function of t, notice, because that's our parameter here. Thanks for watching this video, and see you in the next one.